Hey champ, you ready for bed? You got a long day tomorrow. It's important you get your rest. What's that? A bedtime story to help you fall asleep? Well, all right, here goes. Once upon a time, there was an algebra teacher named Mr. Volel, and he said to his students, "Hey, you want to do some word problems with quadratics?" And the students said, "No. God, no. Please, no." And so he said in response, "Aw, come on, but it'll be fun." And they responded to him saying, "Please, make it stop. Don't make us do word problems, Mr. Volel. We'll do anything." And he said to them, "Anything? Even more word problems?" And then they started crying, and he started laughing, and everyone lived happily ever after. The end. That's right, my darlings. We are finally putting Unit 9 to bed with our last class of our penultimate unit. Let's talk for the last time in Unit 9 about problem solving with quadratics. The idea being, of course, that we know how to solve our problems abstractly. Now that we have all of these tools in our toolkit, we want to see how we can use them to solve some problems like this one. In their newest death-defying trick, a magician plans to escape from a glass box slowly filling with water. The box is 10 feet tall, with a rectangular base 1 foot longer than it is wide. To fill the box completely, a total volume of 290 cubic feet of water is needed. We want to know, what is the width of our box? So let's think about our 5-step checklist, right? Is there a visual that could be helpful? What's my variable going to represent? How can I take this information, build an equation, solve it, and make sure in context that my answer makes sense? Give yourself a couple minutes, play around, try it out, see what you come up with. Once you think you've got something, come back and check it with me. Go! Okay, well, let's get started here with a diagram. One thing that you'll notice about this diagram that's maybe a little bit wonky is that we are no longer in 2D. We've entered the third dimension. I've got a box, so I'm going to try my best to draw a rectangular prism. There are a couple of things that I know about this box, so let me mark up my diagram. First of all, I know that it's 10 feet tall. I also know that its base is 1 foot longer than its width, and the width, of course, is the thing that I'm trying to solve for. So there is my variable. We'll call it W. Based on this, I know that one of my dimensions down here should be width. Maybe I'll say this guy is W. If the other one is 1 foot longer than that, well, then this guy should be W plus 1. The last piece of information that I have not used is that my volume is 290 cubic feet, which means I need to know how to calculate the volume of a rectangular prism. Well, if I have its length, width, and height, that shouldn't be too hard. What's my formula here? 5 seconds, go. Blast from the past. 4, 3, 2, 1. Well, hopefully you remember that if I take my length, multiply by my width, multiply by my height, I get that volume. Now all that remains to do is to slot everything into place. Well, my volume is 290. I've identified my length as W plus 1. Multiply that by W and by the 10 for my height. And there's my equation. Now, if you haven't already, give yourself a couple of minutes. Let's solve this equation for W. If you're still watching, I'm going to assume that that means that you have already done your due diligence and solved for W. Let's do it now together. Now, there are a couple of first moves I could make. I could distribute everything out, but I want to be strategic. Notice that 290 is a multiple of 10. So I'm actually going to begin by dividing both sides by 10 to cancel out that 10 on the right side, which would just leave me with the W plus 1 times W. On the left, that's just 29, and now I'm in pretty nice shape. Either way, I probably want to begin, just like usual, by getting rid of my parentheses. And from here, whether I solve by factoring or by using the quadratic formula, I need a 0 on one side. Here, W squared plus W minus 29 should be on the other. Now, the thing about this guy we'll hopefully notice really quickly is that it's prime. 29 is a prime number. It's 1 times 29. There is no way that I'm getting that 1 in the middle if I try to factor, which means that my quadratic formula is going to be my method of choice. Now, I need to identify my values of A, B, and C. I'm also going to make the bold assumption here that you have already committed that quadratic formula to memory, so I hope you don't mind me omitting writing it out here. Now, in this problem, my a at the front is 1, my middle coefficient b is also 1, and negative 29 is my constant term, which means using my quadratic formula, the values of w should be equal to negative 1 for b, plus or minus the square root of 1 squared for b, minus 4 times a for 1 times negative 29 for c, all over 2 times 1 for a. Let's simplify and see what we get. Well, I've got here negative 1 plus or minus the square root of 1 squared, which is 1. Negative 4 times 1 is negative 4. Negative 4 times negative 29, it turns out, is 116, all over 2 times 1, which is 2. So I've got negative 1 plus or minus the square root of 117 all over 2. And while I wouldn't necessarily expect you to notice this immediately, it does turn out that 117 is the product of 9 and 13. And I, of course, like that if I want to use a radical, re-representing this here by the product property as the square root of 9 times the square root of 13. I can now simplify even further. 3 root 13 should be equivalent to the square root of 117. Now this, if I were solving abstractly, would be my final answer for w. But I'm not abstract here. I'm in the context of a problem, which means I need to make sure that my answer makes sense. Which tells me that just like last time, it might be helpful to split this up. Why not? So let's take this. I'm going to write my two cases. Either here, my value of w is negative 1 plus 3 root 13 over 2, or my value of w is negative 1 minus 3 root 13 over 2. In context, can you tell me if either of these doesn't quite make sense, and if not, why not? 10 seconds, go. Alrighty. Well, if I look really closely at this one on the right, if I take negative 1 and I subtract something, there is no way that this number can be positive. So this friend, unfortunately, must be omitted from my solution set, which does make negative 1 plus 3 root 13 over 2 my final answer. By the way, if you're curious, you could plug this into a calculator. This is approximately 1.30 feet, which in context makes a lot of sense. If I were to take the other one, I'd get something that's negative. We know that our dimensions cannot be negative, so the one on the left is our only viable solution. Beautiful. Now there's one more thing that I would like to introduce you to in the context here of problem solving. One place that's pretty cool and pretty powerful, especially when we get into physics, that our quadratic equations show up is actually when it comes to what we call projectile motion. As it turns out, if I take an object and I throw it into the air, its trajectory will take the shape of a parabola. The equation of that parabola, by some miracle, always turns to be represented by the following formula. We say that y is equal to negative 16 t squared plus vt plus h. And each of these variables here, v, h, t, and y, stand in for something in the context of this problem. V stands for velocity, and velocity is just a fancy word for speed. In other words, I want to know, right, how fast was my object launched? We usually measure this quantity in feet per second, the same way that we might use miles per hour. H here, if I also want to know how fast I was initially launched from, I might want to know how high I was initially launched from. So this guy h is my initial height, usually measured in feet. T is going to be a measure acting a lot like x for time. So we say that t is going to represent the amount of time that our object spends in the air, which we conventionally here measure in seconds. And the last thing that we need to know, this guy y, if I plug all of these values for v, h, and t in, y will actually tell me the height of my object after those t seconds have passed. That height, of course, should be measured in feet. Now that's all well and good. Let's try it in context and see if we can make some sense of how it works. A softball player hits a ball directly upwards from ground level at a rate of 96 feet per second. We want to know the maximum height that our ball will reach. So think creatively here. If I want the maximum height, what on the parabola, hint hint, wink wink, nudge nudge, am I really looking for? And is there anything else here in this problem that seems like useful information to me that I can use in the context of this formula? Give yourself a minute. Play around, see if you notice anything. Think about what we're really solving for. And maybe if you think you've got it, slot into your formula and try to solve your equation. Go! Okay. Well, let me give myself a little visual here. I know I'm going straight up, so there's not really any left or right movement happening here, but I'll draw my parabola in just to help me orient myself. Let's say that here's my ground level, and then I have my ball that's going up and coming back down. If I want the maximum height, that would happen right over here, which, if I'm thinking contextually, really means that what I want is the vertex of my parabola. And I know how to find the vertex of a parabola. Well, it's going to be halfway between my x-intercepts. The only thing here is that my x-intercepts are really going to be t-intercepts because the value here for t is acting like our value of x, but the goal is still the same. If I can find my x, or in this case t-intercepts, take their average, that gives me, in this case, the t value for my vertex, and if I plug in that value for t, I'll get its height, which is measured by y. The last thing that I need to know is what my other values are. Well, if I'm at ground level when I'm initially launched, that means that my launch height, h, should be 0. And I also know if I'm at 96 feet per second, right, there's my velocity, my speed, which should be 96. Now, taking this formula, y equals negative 16t squared plus vt plus h, all I need to do is slot into place. So I've got y equals negative 16t squared plus 96 for v times t plus h, which is 0. I hope you agree that that means we can functionally ignore this guy in context. The last thing that I need to know is that if I'm finding my x, or in this case t-intercepts, there's a particular choice that I'm trying to make. What is it? 5, 4, 3, 2, 1. Well, I know if I want the place where I'm on my horizontal axis, I've got to make y equal to 0. So let me plug in that 0 for y. Now my new equation is negative 16t squared plus 96t. Let's solve for t. If you haven't already, give yourself 2 minutes, pause the video, solve for t. If you have already, I'm assuming that you're here because you've done it. Let's now do some solving together. Well, the first thing that I notice here, I've got a 0 on one side. The right side looks mighty factorable to me. 96, as it turns out, is 16 times 6. So if I'm starting by looking for a greatest common factor, I can take a 16 out of both of these terms. Notice that they also both have a t in common, so 16t is my greatest common factor. To make my life a little bit easier here, I'm going to factor out negative 16t, just because I usually like when the thing at the front inside of my factor is positive. Negative 16t, to get to negative 16t squared, I need to multiply by t. If I factor out a negative 16t, that should leave me with negative 6 in my 96t. Here are my two factors. And now, I've factored one side, I have a 0 on the other. This is prime 0 property real estate. Let's take my two equations here. I'm going to divide by negative 16 in the equation on the left to get my first t-intercept at 0. I'm going to add 6 to both sides of the equation on the right to get my second t-intercept at 6. Now I know that I am interested in finding the vertex of this parabola. Well, to find the vertex, its x value, which here is really t, is going to be the average of 0 and 6. Well, 0 plus 6 is 6. 6 divided by 2 is 3. So at 3 seconds is when I should be at my maximum height. If I take that value for seconds and substitute into my equation, I should be able to calculate that height, y. So I know that y here is going to be equal to negative 16 times t, which we've identified as 3 squared, plus 96 times that guy, 3 for t once again. Let's simplify. Well, I've got negative 16 times 3 squared. 3 squared is 9. And then 96 times 3, it turns out, is 288. Negative 16 times 9 is negative 144. And if I add these two numbers together, 144 feet should be the maximum height of my softball. Very nice. So I'll let you go. We've got one more that I'm going to show you. This will be our warm-up the next time that we meet. But that's a next time that we meet problem. For now, I'll set you free. Have a lovely rest of your day. Thank you for bearing with me in Unit 9. And I will see you one more time for the last time in Unit 10. Okay, goodbye.